Hi everyone! Today we are going to discuss about operating automated hematology analyzers and the principles behind them. Automation provides greater accuracy and greater precision as compared to performing manual methods. In the 1980s, instrumentation has virtually replaced manual cell counting, and many companies have already marketed multiple instruments that can be used inside the hematology laboratory. These analyzers typically provide the 8 standard hematology parameters that are seen in your complete blood count, plus a 3-part or 5-part differential leukocyte counting that can be performed in less than a minute using 200 microliters of whole blood. The good thing about automation is that it allows more efficient workload management and more timely diagnosis and treatment of disease, which is actually the target of the laboratory works or procedures performed inside the hematology section. Now let's try to talk about the instrumental principles behind the different machines used inside the hematology laboratory. Instrumentation and the automation of procedures continue to increase inside the hematology lab. The counting of cellular elements like red blood cells, white blood cells, and even platelets can be based on the following methods. We have electrical impedance, optical scatter, and we also have radio frequency. As we go on with our discussion for this topic, let's try to take a closer look at the different methods and how they are able to detect the presence of the cellular elements. The first principle is the electrical impedance principle. This was originally developed by Coulter Electronics, and it's also referred to as the Coulter principle. Now, what is this all about? The number of cells and their size are determined by detecting and measuring changes in electrical impedance or resistance produced by these particles as they pass through a small aperture. Particles like your red blood cells, white blood cells, and platelets are non-conductive in nature, but they are suspended in an electrically conductive diluent. As a dilute suspension of cells is drawn through the aperture, the passage of each individual cell momentarily increases the resistance of the electrical path between two submerged electrodes that are located on each side of the aperture. This is how the machine determines the number and the size of each individual cell. The number of pulses generated during a specific period is proportional to the number of particles or cells. Say for example, if there are 16 pulses generated, that is also equivalent to 16 particles or cells detected. The amplitude or magnitude of the electrical pulse produced indicates the cell's volume. On the histogram, the x-axis represents the cell size in femtoliters and the y-axis represents the relative number of cells detected. So this is the histogram. Blood cell histograms are produced by the modern automated hematology analyzers which are routinely used to count blood cells. When properly interpreted, this histogram provides information on many hematological conditions than mere cell counts, helping to narrow down the differential diagnosis at a very early stage. Histogram interpretation needs careful analysis of red blood cells, WBCs, and platelet distribution curves. So basically, the histogram gives us information on two important things, and those are the cell size and the number of cells counted by the machine. The next principle is the optical scatter principle. This is also known as hydrodynamic focusing method of cell counting and cell sizing. It makes use of a laser light. The principle behind this is that a diluted blood specimen passes in a steady stream through which a beam of laser light is focused. As the cell passes through the sensing zone, it scatters the focused light. The scattered light is detected by a photodetector and converted into an electrical pulse. The number of pulses generated is directly proportional to the number of cells passing through the sensing zone in a specified period. Now we go to the characteristics of light scatter. There are two characteristics of light scatter, and we start first with the optical light scatter. Light amplification is generated by stimulated emission of radiation, and there are three independent processes involved here. The first one is the diffraction and bending of light around corner with the use of small angles. Then we have the refraction and bending of light because of a change in speed with the use of intermediate angles. And the third one is reflection and light rays turned back by the surface or an obstruction with the use of large angles. Another characteristic of light scatter is the angle of light scatter, which aids in cellular analysis. So we have the forward light scatter at 0 degree. This one is the diffracted light, which relates to the volume of the cell. Then we also have the forward low angle light scatter at 2 to 3 degrees, relates to the size or the volume of the cell. Next, we have the forward high angle at 5 to 15 degrees. This allows for description of the refractive index of the cellular components. And lastly, we have the orthogonal light scatter at 90 degrees. It produces data based in reflection and refraction of the internal components, which correlate with the internal complexity of the cell. Now we go to the principle of flow cytometry. Flow cytometry is defined as the simultaneous measurement of multiple physical characteristics of a single cell as the cell flows in suspension through a measuring device. Now, what is this principle all about? A suspension of stained cells using fluorescent dyes is pressurized using gas and transported through a plastic tubing to a quartz flow chamber within the instrument. In the flow chamber, the specimen is injected through a needle into a stream of physiological saline solution called the sheath. The sheath and specimen both exit the flow chamber through a 75 mm orifice. This laminar flow design confines the cells to the very center of the saline sheath, with the cells moving in a single file. The stained cells next pass through the laser beam. The laser activates the dye, and the cell fluoresces. The interaction between each cell and the laser beam provides the following two types of information. We have the forward scatter, which tells us about the size of the cell, and the side scatter, which is proportional to the cytoplasmic granularity of the cell. Then we have radio frequency. This one makes use of high voltage electromagnetic current that detects cell size based on the cellular density. The radio frequency pulse is directly proportional to the nuclear size and density of the cell. It is also related to the nuclear cytoplasmic ratio and cytoplasmic granulation. On the left side of the screen, you can see here two different types of signals. You have the radio frequency signal and the direct current signal. The DC signal, it detects for the cell size and volume change of the cell, while the radio frequency signal, it's more on the measurement of cell nuclear volume and complexity. The two measurements can be plotted against each other to form a two-dimensional distribution scatter plot. Now, what are the common types of automated cell counting instruments and the method or principle they employ in counting the different cellular components? First, we have the Coulter instrumentation. This one primarily uses the electrical impedance method of counting and sizing cells. We also have Sysmex instrumentation, which uses a combination of impedance and radio frequency. Then we have Abbott instrumentation that uses electrical impedance and optical measurements. And lastly, we have the Siemens Healthcare Diagnostics instrumentation, which makes use of optical flow cytometry. We also have methods for white blood cell differential determination. We have the VCS technology, which has a single channel that analyzes approximately 8,000 cells in a near-naive condition. The VCS technology actually stands for the following. V stands for volume, which uses direct current impedance, wherein the volume of each cell is measured. Next, C stands for conductivity. Radio frequency penetrates the cell, generating data points for the cell size and cell internal structure. And S stands for scatter, which makes use of a mid-angle scatter detected by a beam of laser light, generating data about cellular granularity and cell surface structures. Another method for white blood cell determination is using the multi-angle polarized scatter separation, or MAPS. This one uses 4 light scatter detectors to determine the cellular features of WBCs. The 4 detectors generate the following signals. First, we have the 0-degree or axial light loss, which is related to the WBC size, followed by the 0-degree to 10 degrees intermediate angle scatter related to the cellular complexity of the cell. Then we have the 90 degrees polarized side scatter related to the nuclear lobularity or segmentation of the WBC. And lastly, the 90 degrees depolarized side scatter, which is related to detection of the eosinophil granules. All of these signals are important in identifying and determining or performing characterization of the 5 different WBCs. Another method for white blood cell differential determination is through the use of peroxidase staining. For this one, white blood cells are fixed, then stained, while red blood cells are lysed. The principle behind this method is that a dark precipitate forms in the primary granules of leukocytes containing peroxidase when a chromogen is added with hydrogen peroxide as the substrate. Now, what is the reaction or the result of the different white blood cells when the peroxidase staining is performed? For eosinophils and neutrophils, they are strongly positive, basically because these WBCs contain a lot of peroxidase. Then we have monocytes. The result is weakly positive. And for basophils, lymphocytes, and blasts, their reaction or the result is negative because peroxidase is not present in these cells. Here are some hematological applications of flow cytometry. This technique can be used for leukocyte differentiation and reticulocyte enumeration. For automated differentials, the following methods can be used. You have electrical impedance or forward light scatter, cytochemistry or peroxidase staining, and the use of the VCS technology. Flow cytometry can also be used for evaluation of the internal cellular organelles and nuclear characteristics, which can be done by using a 90-degree laser scatter, polarizing laser light, and radio frequency. Different technologies are being used by instrument manufacturers to produce an automated leukocyte differential, and these are the following. For Beckman Coulter, they are employing the VCS technology. For Abbott Diagnostics, they are making use of MAPS. For Sysmex, they make use of the radio frequency and direct current. And for Siemens Healthcare Diagnostics, they are using the peroxidase staining, optical scatter and absorption, and for the identification of basophils, they are using the differential lysis laser scatter high and low. Before we end with our discussion for today, let me share to you that although hematology analyzers are more precise and accurate in terms of cell counting and cell identification, there is still nothing that can replace the hard work, the skill, and the knowledge of a medical technologist who knows how to perform the manual methods inside the hematology laboratory. In times when the machine produces high or very low results, that's the time when the medical technologist has to go back to the manual methods and perform them in order to confirm or validate the results released by the machine. Therefore, it is important that you hone both your skills and knowledge not only in performing the manual methods but also manipulating the hematology analyzers inside the section. So you always have to go back to the basics. You have to know the basics in order for you to find your way through the hematology laboratory. So that's it. Thank you for listening, and I hope you have learned a lot from this discussion. I hope to see you next time and have a good day.